Swayam Prabha. Digital India. Educated India.
So, in the last lecture what we have studied is the inverse Laplace transform, its properties, and also the applications of those properties for solving various kind of problems. The last lecture we stopped at multiplication by power of s. Now, let us see the division by power of s. The theorem says that if f t is sectionally continuous and of exponential order a such that limit t approaches 0 f t by t exist, then for s greater than a, Laplace inverse of f s by s equals 0 to t f x dx. That means, if your f s is replaced by f s by s, then that will be there the function will become integration of the function 0 to t f x, provided limit t approaches 0 f dash f t by t exist. This is required. Let us see the proof of this. Suppose your g t this equals 0 to t f x dx. I am assuming f t equals this. So, that from here very safely you can tell g dash t this is nothing but f t, and also g 0 will be equals to 0. So, if I take g t equals the function 0 to t f x dx, then I can tell g dash t equals f t and g 0 equals 0. Now, what is Laplace transform of g dash t? Laplace transform of g dash t is s Laplace transform of g t, just using the properties minus g 0. We know this thing, and g 0 is 0. So, that you can simply write it s this is equals s Laplace transform of g t, or in other sense you can say that your f s is equals to Laplace transform of g dash t, which is f s, basically because g dash t is nothing but f t. So, Laplace transform of f t equals Laplace transform of g dash t equals f s, and this f s equals you are writing is Laplace transform of g of t. Therefore, you can tell that Laplace transform of g t this is equals to f s by s, you can write down. Once I am writing this, so you can say that Laplace inverse of f s by s this equals g t, and what is g t? G t is nothing but this one. So, g t is nothing but 0 to t f x dx, and this completes the proof of this particular theorem, that if this is given, then Laplace inverse of f s by s is equals to 0 to t f x dx, where Laplace inverse of f s is equals to f t. So, let us see here the your g t we assumed only, and we assume g dash t equals, once I am assuming g t is 0 to t f x dx, we can say g dash t equals f t and g 0 equals 0. So, that Laplace transform of g dash t equals s into Laplace transform of g t. From here we are writing f s equals s into Laplace transform of g t, and we are getting the required solution over here, that is this one. Now, let us come to a very important property of Laplace transform. This property belongs to various places. I will discuss it with respect to the Laplace transform, and later whenever we are going for the other transforms. This property we call it as the convolution property. Suppose f t and g t be two functions of class A. Please remember, class A means they are piecewise continuous and they are of exponential order A. So, if I have two functions f t and g t like this, then the convolution of two functions f t and g t denoted by f star g, please note this one, this we read as f convolution g, although we have given the notation as star, f star g or f convolution g, which is denoted by f star g equals 0 to t f x into g of t minus x dx. So, therefore, if I have two functions f t and g t, they are of class A means their Laplace transform exists. From there we are specifying this. Then the convolution of these two functions f and g denoted by f star g, this is equals to 0 to t f x into g of t minus x dx. It has certain properties which can be proved very easily. F star g is commutative, that is f star g equals g star f. I am not giving the proof because the proofs are simple. Property 2, the convolution with respect to the functions f and g are associative, that is f star g star h equals f star g star h. So, the convolution is associative also. And third one is f star g is distributive only with respect to addition. Please note this one, f star g is distributive with respect to addition, that is f star g plus h, this is equals to f star g plus f star h. So, f star g plus h, this is equals f star g plus f star h. So, please note that the convolution which we have defined earlier, this one, because convolution plays a vital role, f star g equals 0 to t f x into g of t minus x dx, and it satisfies these three properties. The convolution is commutative, associative and distributive with respect to addition only. There is a well known theorem which we call as convolution theorem. Let f t and g t be two functions of class A, that is Laplace transform of them exist, and if Laplace inverse of f s is f t, Laplace inverse of g s is capital G t, then Laplace inverse of f s g s, this is nothing but f star g, that is 0 to t f x into g of t minus x dx, or in other sense Laplace transform of convolution of two functions. If I have to take in the simple words, Laplace transform of convolution of two functions is equals to Laplace transform of the function f t into the Laplace transform of the function g t. So, this one is very important, that if I have the convolution of two functions, then Laplace transform of convolution of two functions equals Laplace multiplication of Laplace transform of those two individual functions. Let us see the proof of this. Let us assume that 0 to t f x into g of t minus x dx, this is equals to h of t. We are assuming this. That is, we can say that Laplace transform of this is nothing but f star g, this one is nothing but f star g. So, f star g is this, f x equals h t. Now, Laplace transform of f star g, this I can write it as Laplace transform of h t, and this is equals, you can write down 0 to infinity e power minus s t into 0 to t f of x into g of t minus x into dx into dt. So, basically I have to find out evaluate this particular integral 0 to infinity e power minus s t into 0 to t f of x, this is actually x, f of x into g of t minus x dx into dt. To evaluate this, let us introduce a new function u x t. I am saying that means value will be dependent on, value of t will be dependent on x. Say it is 0 for t less than x and it is 1 for t greater than equals x. I am defining a new function u x t such that for t less than x, value of the function is 0, for t greater than equals x, the value of the function is 1. What will be this function then? F x into g of t minus x into u x t, if I multiply by this function into f x into g of t minus x. So, this will be 0 for x greater than t, x greater than equals t, and this will be f x into g of t minus x for x less than equals t, we can write down. Now, the product vanishes for all values of x greater than t. For all values of x are greater than t, then the limit can be extended here. For this, the limit can be extended from 0 to infinity, because I am considering, please see this one, I am considering a new function. I have defined a function this u x t, which is 0 for t less than x, which is 1 for t greater than equals x. And whenever I am multiplying this function, my new function is 0 for x greater than t and is equals to f x into g into t minus x for x less than equals t. Therefore, if I take this function multiplying by this 0 to t limit, now I can make it to 0 to infinity, because for x greater than t the value of the function vanishes. So, therefore, I can write down using this new function Laplace transform of f star g, this is equals to 0 to infinity. This will also be 0 to infinity due to that reason, please note this, f x into g of t minus x into u x t dx into e power minus s t into dt. I am getting this. So, I could do it 0 to t, I could change into 0 to infinity only by introducing this function u x t. Otherwise, I cannot write the 0 to t integration into 0 to infinity. Please note this one. And once both are 0 to infinity, by changing the order of the integration, I can write down 0 to infinity. This is also 0 to infinity f x g of t minus x into u x t into e power minus s t into dt, and then your dx will come. So, once it is dt, this f x I can take out from this 0 to infinity, or in other sense this I can write it as f x into 0 to infinity. F x will come outside, because this is the first integral is on t. So, f x is independent of t. So, if I am bringing f x out, so if I am bringing f x out, g of t minus x into u x t into e power minus s t dt, and then the integration over dx will come. And this equals, again I can write down 0 to infinity f x into g x to infinity g of t minus x into e power minus s t dt into dx. Why I can write down? Because for t less than x, your integrand is 0 and u x t is 1 for t 1, this is for t greater than equals x, we know it. U x equals t, u x t equals 1 for t greater than equals x, and for t less than x, this is equals 0. So, for that reason, this 0 to infinity, now I can break it into x to infinity over here. Now, on this integral, on this particular integral, now substitute one thing, say t minus x equals mu. I am assuming here now t minus x equals mu on this given integral. So, once I am substituting t minus x equals mu, therefore, Laplace transform of f star g, this equals, I can write down 0 to infinity f x is there, this will be 0 to infinity, this will be a function of mu, then g mu into e power minus s into x plus mu d mu into dx. I am changing t to x, t minus x equals mu. So, I am bringing it here. This equals, again you can write it as f x into 0 to infinity g mu into e power minus s mu d mu into e power minus s x dx, because e power minus s x is not coming under this. So, this simply now I am breaking it into two independent variables x and mu, and this equals, I can write it, one integral will be f x into this e power minus s x dx. This will be one integral into 0 to infinity g mu into e power minus s mu into d mu will come. What is this? This is nothing but the Laplace transform of f t. This is nothing but Laplace transform of f t into, this is nothing but Laplace transform of g t. So, we started with Laplace transform of the convolution of two functions, and this equals f s into g s. So, therefore, Laplace transform of convolution of two functions equals multiplication of Laplace transform of both the functions. I hope the theorem is very clear to you, that if I take the convolution of two functions and then if I take the Laplace transform, that is Laplace transform of convolution of two functions, this is equals to the multiplication of Laplace transform of both the functions. So, just quickly whatever I explained, the function is given, I am writing it like this, then I am introducing a new function u x t, which is 0 for t less than x, 1 for t greater than x. Then I am getting this function which I have written already. Now, product vanishes for all values of x. So, therefore, this integral 0 to t can be made as 0 to infinity, and then I am interchanging the order of the integration. Once I am interchanging the order of the integration, then I am getting 0 to infinity f x into this, because I know for t less than x the integrand is this 0 to infinity, I am making it into x to infinity. The reason is for t less than x integrand is 0 and u x t is 1. Then on the last one I am substituting t minus x equals mu. Once I am substituting, and I can break it into two different integrals, where the first integral is nothing but Laplace transform of f t and the second integral is the Laplace transform of g t. So, that and it becomes nothing but f s into g s. So, now let us see using example how convolution of functions are useful in deriving the inverse Laplace transform. That is, if I use convolution, how it becomes easy for us to find out the inverse Laplace transform of different functions. So, you have to find out the Laplace inverse of 1 by root over s into s minus 1. Now, we are assuming that f s equals 1 by root s, g s equals 1 by s minus 1, which implies your g t is obviously e power t. And also you know it, Laplace transform of t to the power minus half, this is equals to gamma half by root s, and this is nothing but then root pi by root s. So, therefore, from here f t also you know it. What is f t, that you can find out from here, t to the power minus half into root pi will come, or in other sense you can tell that Laplace transform of 1 by root pi t, this is equals 1 by root s. From here you can tell. So, that Laplace inverse of 1 by root s, this is equals your 1 by root pi t, and which is nothing but f t. So, once you have the identified here f s, you have identified g s. From g s directly I am finding out g t like this, and from this one I am identifying the root pi by s. So, that f t also I am identifying as 1 by root pi t. So, now f t is known to me, g t is known to me. So, by convolution theorem what you know? Laplace inverse of f s into g s, this is equals 0 to t f x into g of t minus x into d x. So, that 0 to t, what is your f x? F x is nothing but 1 by root pi x, f t was root pi t, into e power t minus x into d x. So, effectively what is happening now over here? You have to now just evaluate an integral to find out the Laplace inverse of the function. To evaluate the integral of this is equals, you can write down e power t by root pi can come outside, 0 to t e power minus x by root over x into dx. If you put here x equals say u square, then this will become e power t by root pi into 0 to x is there. So, it will become root t into e power minus x is there. So, it will be minus u square by u into dx will be twice u du. So, that you can write down 2 will go out, 2 e to the power t by root pi 0 to root t e power minus u square du. And if you remember, this is nothing but the error function which we have done in earlier lectures, that error function of root t is 0 to root t e power minus u square du. So, that I am obtaining this as e power t into E R f of root t. So, the Laplace inverse of f s into g s is coming as e power t into E R f of root t. If you see this one, your original function was Laplace inverse of 1 by root s into s minus 1. You assumed f s as first one, 1 by root s, g s as 1 by s minus 1. From here, you first obtain g t, then using this process, you are obtaining what is the value of f t. Once I obtain the f t and g t, then by convolution theorem, I can write down Laplace inverse of f s g s is 0 to t f x into g t of minus s. Now, substitute the value of f t and g t here and evaluate the integral by following this method, and ultimately you will obtain the result as e power t into error function of root t. Now, let us see the next example, that is Laplace inverse of 1 by 1 plus root s. For this case, what happens? Your problem is Laplace inverse of 1 by 1 plus root s. Obviously, this denominator you cannot handle. So, I have to multiply both sides by 1 minus root over 1 minus s, the normal algebraic operation. So, if I multiply by this 1 minus root over 1 minus s, then it will become 1 minus 1 minus s. So, that it becomes Laplace inverse of root over 1, this will be root over 1 plus s. So, this is equals to root over Laplace inverse of root over 1 plus s minus 1 by s. So, I can write it as Laplace inverse of root over 1 plus s by s 1 minus Laplace inverse of 1 by s I can write down, and this equals, I can simply write down it as Laplace inverse of 1 plus s by s into root over 1 plus s minus this value is equals to 1. This I can break it into two parts again, Laplace inverse of 1 by s into root over 1 plus s plus Laplace inverse of 1 by root over 1 plus s minus 1. And this is nothing but Laplace inverse of this thing is ERF of root t. This also I can find out, so that very easily I can find out the solution of this. So, let me just check it here. So, you are getting this, from here you are obtaining this, we have done this thing. Then I am writing this as Laplace inverse of 1 plus s by root over s into 1 plus s minus 1. This I am breaking it into Laplace inverse form, and from here this first function is 1 by s into root over 1 plus s is nothing but error function. This root over 1 plus s I am writing using property e power minus t into Laplace inverse of 1 by root s, and this you can write down the second term e power minus t into 1 by root pi t minus 1, and ultimately I am obtaining the result as this one. This we will just omitting this example. Apply convolution theorem to find the value of this thing. Since we are doing the convolution, so it will be easy for us to do it. Laplace inverse of 1 by s plus 1, this is equals e power minus t, and the second one was Laplace inverse of 1 by s minus 2, this is e power 2 t. So, that Laplace inverse of 1 by s plus 1 into s plus 2, using convolution theorem you can write it 0 to t f t is e power minus t and g t is e power g of t minus x. So, it will be e power 2 into t minus x into dx. So, this is equals 0 to t e power 2 t into e power minus 3 x dx. So, e power 2 t will simply come outside, e power 3 x, that will be becoming minus e power minus 3 x by 3 from 0 to t. So, that your result will become ultimately 1 by 3 into e power 2 t minus e power t. You will obtain the value as this one. So, using convolution very easily you are writing it as this thing 1 by s plus 1 into s plus 2 0 to t this thing, provided I know the Laplace inverse of 1 by s plus 1 and 1 by s plus 2 separately. Let us quickly see it, and let us see one more example, that is Laplace inverse of s square by s square plus 4 whole square. So, the problem is your function is s square by s square plus 4 whole square. I think I know this thing, Laplace inverse of s by s square plus 4. This is cos 2 t, I know it. Therefore, Laplace inverse of s square by s square plus 4 whole square. This I can simply write it as s by s square plus 4 into s by s square plus 4. So, this is Laplace inverse of f s into g s, and using the convolution theorem this is f t, that is cos of 2 x into g of t minus x, means cos of 2 into t minus x into dx. And now, I have to evaluate this particular integral. This is equals 0 to t cos of 2 x into simple, I can write it cos 2 t cos 2 x plus sin 2 t into sin 2 x dx. And once I am getting this cos 2 t is independent of x. So, that in the next line I can write it, this is equals to cos 2 t into 0 to t cos square 2 x dx plus sin 2 t into 0 to t cos 2x into sin 2x dx. Using trigonometry now, I have to calculate it. So, it becomes 0 to t cos square this thing I can write down 1 plus cos 4x into dx plus half sin 2 t into this I can write it as sin 4x dx. So, that I can evaluate the integrals easily. This will be equals to cos 2 t by 2 will come here, and I am directly writing this t plus sin 4t by 4 plus sin 2t by 2, and the value of this integral will be 1 minus cos 4t by 4. So, once I am getting this, if you wish, you can break it into some simpler form also. So, like this way, whenever I have the product of two Laplace transforms, that is f1s into f2s, always I can use the convolution theorem to find out that to form an integral of the form 0 to t f x into g of t minus x dx, and I simply evaluate that integral to obtain the Laplace inverse of some product of some functions. Thank you.